Hello, I'm Jan, and in this video I'll describe to you our paper named Distributed Graph Problems Through an Automata-theoretic Lens. This is a joint work with Iran Chang and Yuka Suomela. Let me start by giving you a high-level picture of what we are trying to solve. We are given a graph problem pi, and our goal is to design an efficient algorithm that will answer the following three questions. First, is pi solvable for any graph? Second, can pi be solved efficiently? And third, what is an optimal algorithm for solving graph problem pi? Of course, this is a very broadly posed question, so in our paper, we studied the following special case. The graph problems that we focus on are locally checkable labeling problems. These problems are, for example, computing vertex coloring of a graph, giving consistent orientation, or maximal matching. Moreover, we require that the graphs where we want to solve such problems are only unlabeled paths and cycles. These graphs can be either directed or undirected. The reason for this restriction will be explained soon. On the output side, we give the answers for the local model of distributed computing. In this model, the input graph also describes the communication network. Each node has a unique identifier of the order of log n bits, and in each step, nodes can exchange arbitrarily long messages with their neighbors. The key measure in this model is the round complexity. Round complexity measures the number of rounds required until every node has finished exchanging messages. Hence, lower the complexity, the more efficient the algorithm is. Now, as I have defined the setting, I can describe why we have picked to study cycles and paths. From the prior works, we know that in the local model, problems on cycles and paths are either constant round solvable, log star solvable, or global. But the proofs establishing this classification do not give us any algorithm how to classify a specific problem. So it is a very natural direction to see how efficiently can we do it. As a first step, Brandt et al. Showed that the case of unlabeled directed cycles has a simple characterization. But in the same paper, they also show that already in the case of 2D grids, efficient classification is impossible. In fact, it is undecidable to determine a round complexity of a given LCL problem. Recently, Badiou et al. Showed that the same question is already p-space hard for labeled paths. So it is unknown whether it is possible to efficiently classify problems on cycles or paths, or whether it is already hard. Moving on to results, let me tell you what we have obtained. Most importantly, we give an affirmative answer and show that indeed, almost all questions on cycles and paths can be answered by a polynomial time algorithm. Such algorithm answers, first, solvability of a problem pi in all except one case. For such case, we prove an NP hardness result. Next, it gives the round complexity of pi without any exceptions. And finally, we give a way how to construct an optimal distributed algorithm for solving pi. The way how we have obtained the results is by designing a uniform automata-theoretic formalism for the LCL problems. In the rest of the talk, I'll explain to you how to see an LCL problem as an automaton, and afterwards, how does it characterize the LCL. So, how to see an LCL problem as an automaton? First, I need to briefly explain you the LCL formalism. For representing LCL problems, we chose node edge checkable formalism. In such formalism, we imagine that each edge is split in two halves, and the task is to label the half edges according to some constraints. To illustrate the formalism, I have picked two LCL problems. I chose edge coloring on the left and consistent orientation on the right. They will be our running examples for the whole talk. The constraints that define an LCL problem are divided into node and edge constraints. The node constraints represent allowed labels next to any node. Hence, for tree coloring, it will be any combination of different colors. Similarly, the edge constraint represents allowed labels for the whole edge. Hence, we see that the edge tree coloring has only 1, 1, 2, 2, and 3, 3. For the consistent orientation, we have two labels, head H and tail T, and from the constraints, we see that they need to keep alternating. As we are considering only cycles and paths, the constraints are just pairs of allowed labels for both node and edge constraints. To summarize, an LCL problem is described by the node and edge constraints, and such formalism is as expressive as the classical definition given by Nauer and Stockmar. The next step is to turn such description into an automaton. In our case, it will be a non-deterministic automaton over a unary alphabet. How does it look like? The connection is very natural given the formalism I have just explained. We identify the states of an automaton with the edge constraints and the transitions with the node constraints. Again, let me explain it on the examples. The automaton for the edge coloring will have just 3 states. These states will be 1, 1, 2, 2, and 3, 3. For the transitions, they'll be between any 2 states. But because it has to be a 3 coloring, it doesn't have any self-loop. In the case of consistent orientation, we'll have just 2 states, and these states will have a self-loop. To summarize, by the above procedure, we can see any LCL problem as an automaton. Next, I'll show you how to use this automaton to characterize the LCL problems. It will be a 3-step process. As a first step, we classify each state of an automaton into one of the 6 types. I'll now describe you the first 3 types, as the last ones are just variations of the previous ones. First, repeatable state is a state to which we can return. Second, a flexible state is a state to which we can return in exactly k steps for any big enough k. And third, a loop state is a state which has a loop. For the next 2 types, we need a definition of a mirror. Mirror of a state is just a state with flipped label pairs. For example, a mirror of state 1, 2 is 2, 1. Now, for the types, a mirror flexible state strengthens the flexible state to moreover reach its mirror in exactly k steps. And the mirror flexible loop just combines the loop and mirror flexible type together. Again, let me go over our 2 running examples. Let's look at the case of 3 coloring and, for example, pick state 1, 1. To this state, we can return in 2 steps by e.g. node 2, 2, and also in 3 steps using both nodes. And by combining these returning blocks, we can return to 1, 1 in any number of steps, so such state is flexible. In this case, it is also trivially mirror flexible. For the consistent orientation, each node has a self-loop, so it is a loop state. But as they cannot reach themselves, they are not mirror flexible loops. In the paper, we show that all such types can be computed in polynomial type. Non-trivial cases are flexible types. As a second step, we determine a type of an automaton based on which states the automaton has. To have a full characterization, we need 13 types. These types fully determine solvability and round complexity, which will be shown on the next slide. I'll not go over the whole table, but only explain how to classify the 3 coloring and consistent orientation. For the 3 coloring, it has a mirror flexible state, but not a mirror flexible loop, hence it will be the type E. For the consistent orientation, it has a loop, but this loop is not a mirror flexible loop, hence it will be a type C. And now, finally, we have everything needed to answer the solvability and round complexity. The 3 coloring is a set of type E, so it will be log-star solvable in both directed and undirected case. And for the consistent orientation and any type C problem, it is trivial in the directed case, but requires n rounds in undirected case. Interestingly, from such characterization, we also obtain the converse. That is, any log-star solvable LCL problem in undirected case has to have a mirror flexible state. And the constant time solvable problems in undirected case have to have a mirror flexible loop. Now we have proceeded to an end, so let me summarize the talk and our paper. The task was to design an efficient algorithm for characterizing LCL problems. We show that it is indeed possible, in the case of cycles and paths. The key technique was to represent LCRs as automata. Given such automaton, we can easily answer solvability and round complexity. In the full version, you can find how to synthesize an optimal algorithm using automata, the connection with directing words, and also the extension to rooted trees for a special case of LCR problems. I'll be happy to answer all questions during this session.